Hi, welcome to San Francisco's Exploratorium. I'm Robin Higdon, and joining me today in the studio is my co-host, Ron Hipschman. It's been a couple of years since we last reported on our journey to Mars. We reported on the current situation of the Mir rovers, but today we're here to celebrate the launch of an exciting new robot to Mars. Ron, how'd the launch go this morning?
Well, I got up really early this morning because it launched at about 7 o'clock in the morning. It was early for me, but it was an exciting launch. It was well worth it. Before we actually show you the launch, though, let's describe it real quickly. I have a diagram over here, which we can put up on your screen. The liftoff happened at about 7 o'clock. About 2 minutes later, the solid rocket boosters jettisoned, and about 3.5 minutes later, the covering over the spacecraft ejected, because they were pretty much out of the atmosphere at that point. They were 74 miles high. A few minutes later, at 4.5 minutes, the first stage separated from the upper stage. The first stage is called the Atlas. The upper stage is called the Centaur. And then the Centaur burned for about almost 7 minutes. And then they cruised for a little while. And then they lit the Centaur back up again for 8 minutes. And at that point, they cut that off, and the spacecraft was moving fast enough to get it to Mars, but it was still attached to that second stage. And so they reoriented the second stage and spun the spacecraft up, and then they separated the two at about 42 minutes in. And so we're going to take a look at both live video and some animation that NASA has provided to us. So let's just go right to the launch video right now.
15 seconds.
So here's the Atlas Centaur sitting at Launch Complex
10,
41.
9, 8, 7.
It's on the military
6,
side of Cape
5,
Canaveral, not on the
4,
civilian NASA side.
3,
Those 4 towers
1.
are to
Main engine start,
attract
0,
lightning
and
instead of the spacecraft. They want the lightning
Atlas
to hit the 4 towers. So there we are, launch.
Seeking clues
Wow.
to the
That's
planetary
beautiful,
puzzle
Ron. Now, you've
about
been to
life on
launches.
Mars.
What's it like to be there?
If you're at a launch, it's pretty dramatic. I've been to 2 shuttle launches, and the shuttle launch, we were sitting about 3 miles away, which is as close as you can get, as close as NASA allows you. And you see this really bright light happen off in the distance. It's incredibly bright, and this large thing rises on that plume of smoke, and you don't hear it for about 15 seconds because you're 3 miles away, and sound travels at 1,000 feet per second, so that's 15,000 feet. But when you do hear it, you really hear it. It rumbles, and it gets that crackly sound because the gases are moving faster than the speed of sound, and it's a really dramatic thing. So coming up here, you're going to see fairly soon on our video, you'll see the solid rocket booster separation. That happens only a couple minutes in. Those solid rocket boosters don't last for long, but they're very high thrust. They get the rocket moving very fast, very quickly. High acceleration.
And why do you need so much intense acceleration at launch?
Well, there's a lot. Gravity on the Earth wants to hold everything to the Earth, and so you have to have a lot of lifting power. You realize that spacecraft weighs a lot. Even just the rover itself weighs 2,000 pounds.
Wow.
And so to lift that into orbit and then to get it completely away from the Earth takes a lot of energy.
So right now, those 4 boosters, they're burning through their fuel to the point where there's none left?
Right. They're sort of like a 4th of July rocket. They have solid rocket fuel. And here you're going to see them fall away, because they're burned out now.
So it just gets rid of the extra weight.
Right. There they go.
Where do they go?
1, 2, 3, 4. Those fall back into the ocean and can be recovered and reused, just like on the shuttle.
Gannon, our United Launch Alliance.
And now you can see the Atlas boosters are now lifting the spacecraft farther and farther into orbit.
And how long is it before it's sort of on cruise control, where you don't need all that extra thrust?
Not long. It's about 45 minutes in, and the spacecraft is just cruising. Literally, there's no power. We'll see that. The next thing to happen here, you'll see, and they'll change cameras eventually to a camera that's actually on the booster itself. The fairing, the covering over the spacecraft will come off.
So there's actually a camera on the rocket itself?
On the rocket. And I'm sure that NASA will provide a lot more video as soon as they have a little bit of time. There's the rocket. the video on the rocket.
And where is this rocket now? It's been hours
Oh,
since
it's
it
probably
was
somewhere
launched.
between the Earth and the Moon.
Hasn't reached the moon yet.
Well, not the rocket, just the spacecraft.
Of course.
Now we're hitting our 2.5G one coming up on payload.
Going farther and farther away.
Yeah.
Edison.
There we are back looking at the spacecraft.
It seems so still. I'd expect to see a lot of shaking on the rocket.
Well, the camera's attached there. We just shut down the... There goes the fairing.
Wow.
And we also have a successful CFLR jettison.
And now the Centaur is going to fire up again. I mean, sorry, the Atlas is going to fire up again for a little while.
So there's a whole series of rockets that fire, they get released, they refire.
And we are now
constant propulsion.
That's right. We're coming up here in a short bit. We're going to see the separation of the Atlas first stage from the Centaur second stage. But you can see it's getting pretty far out there. We're really only seeing a dot. It's kind of, when you get to this stage, when you're actually at the Cape, you have your cameras pointed, you're kind of watching this dot in the sky. It gets a little less interesting.
Expecting BECO in 10 seconds.
Here, so there we are now looking
Safety ADUs.
again.
And this is real footage. This isn't an animation.
This is real footage.
A couple hours ago, actually, on the rocket as it was
BECO,
leaving Earth.
Retro rockets and stage separation.
Wow.
So there we had the separation. Now the Centaur, the upper stage, is firing. And you'll notice that the first stage, Atlas, is going to drop away.
And full thrust. Centaur main engine is up and
Is that
running.
it?
There it is. Yep.
And that just falls back into the ocean?
Falls back to Earth. So we can't see much more except in animation. So we have an animation that we can show that NASA has provided. So, and that's going to show us up to the point where the spacecraft separates from the Centaur stage. Let's just do that right now.
So we'll just show you the rest of it. But again, this is an animation. This
Right.
isn't actually real footage. What we saw was real. This is an animation.
So here it is. The Centaur stage just shut down, and is now going to reorient the orbiter. The orbiter's on top there, that cylindrical thing with the cone.
And is it doing this automatically?
And it's now going to spin it up. See, it's spinning a little bit. That spinning is gyro-stabilizing the spacecraft. And now it's separated from the Centaur. The Centaur is going to actually turn backwards and fire its rocket for a little longer and then head back down into the atmosphere of the Earth. Now the spacecraft is headed out to Mars. It's on pretty much autopilot. They can do a little bit of course correction. See the solar cells on top of that cruise, that round section, that's going to be ejected eventually, but those solar cells power it till it gets to Mars.
So it's solar powered until it gets to Mars. And I was asking you too, is there live?
It's actually solar and nuclear powered.
Both.
Both. Yeah.
Okay. So we'll talk about this, the power on the rover later.
Mm-hmm.
But is this all run by the computers? You know, is this all done in advance, or is there any live control happening?
All of that is pre-programmed.
It's all pre-programmed. Okay, so this is not by any means our first trip to Mars. As I was mentioning, of course, the famous MERS that were launched some years ago. But actually, we have a long history of Mars rovers. Do you want to go back to this?
Let's just go back real quick, because I want to show you a diagram of how we get to Mars, what the actual orbit looks like. So here we have the orbit of Mars, of Earth, which is, here's the green Earth, and it's orbiting here on the inner track. Mars is orbiting on the outer track. Sometimes Mars and Earth are close, sometimes they're far away. But here we have the Earth at launch. Now, the launch could have taken place any place in this beige area right here, but we actually got the launch off as really, really early on the 26th of November. It could have launched yesterday, but then the spacecraft will follow this path to Mars, and Mars is here at launch, but Mars is here in 8.5 months, and hopefully the spacecraft and Mars will be at the same place in 8.5 months, and Mars will actually be able to enter into the atmosphere of Mars. There's a couple of mid-course corrections it can do on the way, just in case. So let's talk about those earlier missions.
Okay, I really wanted to get to the early missions, mostly because I feel tied to these things, because our first Mars mission was in 1965, which happens to be the year that I was born. So the Mars program has been going as long as I've been alive. And to sort of give us an update and sort of tell us how we've gotten to this great point, we have our senior scientist, Paul Doherty. Paul, thank you so much for joining us today.
Thank you, Robin and Ron, for that introduction. And I'm going to take you back to 1965, where we sent Mariner 4, a solar-powered spacecraft, to just fly past Mars. It had one of the world's first digital cameras.
What?
40 kilopixels. That's 200 by 200 pixels. And the images, I was in high school, and when the images came in, I was crushed. I had grown up with canals on Mars. And the first image, which you'll see here, was just a dead world with craters. And look at the quality of the 200 pixel by 200 pixel image. We've come a long way. The cameras you can buy today are 1,000 times better. But this was 1965. Well, we went again to Mars, several more missions, and one of my favorites was Mariner 9. And in this Mariner 9 image, you can actually see things that look like rivers running down into craters and leaving deposits. That's exciting. The idea there might be a fluid flow on Mars, maybe water.
Now, these are just orbiters. These aren't...
This orbited, that's right. Yeah,
yeah,
so this one actually fired its rockets and went into orbit of Mars and took these wonderful images which inspired future missions. Well then, on the bicentennial, let's go on to the next one. The bicentennial, one of my favorites, Viking, 1976, landed on Mars. It couldn't go anywhere. It just had a big arm that reached out and sampled the surface looking for life. We were really ambitious. Let's go find life on the first try. We didn't. But we did see something interesting in the next image. And I was actually, by that time, I was a Mars scientist doing research on the Viking mission. So this is my favorite image as a researcher. It woke up one morning early in the winter, and the ground was covered with snow. Snow! Well, it turns out that snow condensed at night at 140 Kelvin. That's minus 200 Fahrenheit. And that's the temperature on Mars at which carbon dioxide ice, dry ice like I have in this container, condenses out of the atmosphere into snow. But the snow hung around when the temperature warmed up. It didn't go away. So what happened is exactly what's happening in this tray. I put some dry ice in this tray, and it condensed water vapor from the atmosphere, and that's the white particles on the outside. So now, from an image, we know carbon dioxide on Mars got cold enough to freeze out, and that triggered the formation of water snow. Very exciting information. Next. So we went there. We went there with a tiny rover bigger than a bread box. The Sagan, this is the Pathfinder mission, the Sagan Memorial Station, the Sojourner robot, went out there and it stuck its nose, its probe against the rocks to find out what the rocks were made of. We're starting on Mars with rocks. Next. So it puts its nose right up, this little teeny rover, but it's got the classic 6 wheels that all future rovers used. Next.
Wasn't this rock called Big Joe?
I think that's Big Joe, yeah. And stick your nose on Big Joe. Okay, next image. So this is the whole map of what it did. It just stayed right there near the station, went around, probed rock after rock, but that proved the principle that we could make a rover on Mars. This one landed with airbags. They just dropped it onto the surface with an airbag that bounced around, the airbag deflated, it opened up and rolled away. That prepared the way for, and here's the picture it took of itself, but that prepared the way for rovers, and here's a model of the rovers, solar-powered. They landed 7 years ago, and one of them, Opportunity, is still running. It's an amazing rover. Solar-powered, got cameras on the top. Next. That's a fake image. Here we are in this very studio with a full-size model of that rover, and you can see its eyes, its cameras are just about as high as I am. Next one. And these are self-portraits from the mast looking down on the rover itself. This is the picture of the rovers on Mars, Spirit and Opportunity. Next.
It looks a lot of dust on the solar cells.
Oh, that's right.
Spirit.
The solar panels are limited by the dust. They thought that's what would kill the rovers, but on Mars there are dust devils which periodically clean your solar panels, like having a little gas station attendant there. Next. The rover has an arm as well. It could not only roll, it could reach its arm out and drill into rocks and use probes to find out what the rocks were made of. Next. And here's a fake image. That's a real image of a Martian crater, but we've photoshopped in the rover there on the rim. And the rover rolled down the slope here, and just like a road cut on Earth, that crater cut into the old rocks on Mars. It did a history of the rocks on Mars. And while the rovers were there, they found rocks that had been altered by groundwater. They found that rocks that in the past had had water on them. And that's what they were really there to find. So it was a successful mission. Next. Well, we also went with a lander, Phoenix lander, up near the Arctic on Mars, looking for water. We're taking this a step at a time. The Phoenix landed in the Arctic. Next. Took a self-portrait, as they all do, looking down. You can see the solar panels and the dirt around it. Next. But the first image it took was called the Holy Cow image, because they went there looking to hopefully find some ice. The retro rockets, as it landed, blew away the surface, and the width of your fist underneath the soil, it was solid water ice. The Mars really has water ice in tremendous quantity up in the polar regions. And they found it in the first image they took. That's spectacular success on a mission. The very next winter, the snow buried the rover. The snowfall killed it, broke off the solar panels. That's what you get if you go to the Martian Arctic. Next. So it took its arm. It had an arm. It dug 2 trenches. Right in the soil, they found water ice. And after 4 days, some of the water ice had sublimed. After 10 days, it had all gone away. So we know that there's ice in the soil of Mars. Next. Not at all latitudes, only in the Arctic. And so here's a final image showing the family of rovers. You see the little Pathfinder here. And then the quite a bit bigger 5-foot-high Mir, the Spirit and the Opportunity. And now this is the size of the Curiosity rover, big as an SUV. While we're going on to our next program, I have with me the smells of Mars. This bottle is full of dry ice, and it's outgassing carbon dioxide. If you're brave enough, you can take a gentle sniff and get a smell of what it's like to be on Mars, and this will knock you out. It's really a powerful smell. It's carbon dioxide straight, and Mars's atmosphere is carbon dioxide. So now, Ron, take us away and show us the rover.
Okay, we get to go a little further now. What we want to talk to you now about is getting to Mars and what we're putting on the surface of Mars. So that package that you saw at the end of the last video, on its way to Mars right now, probably between the Earth and the Moon somewhere, is a spacecraft that's made up of about 5 parts. And here in this slide, we have a sort of an exploded diagram of the spacecraft. So the 5 parts from the top to the bottom are the cruise stage, and this is the thing that has the computers and the retro thrusters that'll do the mid-course corrections on the way to Mars, but it's not part of the thing that's going to land on Mars. Below that, there's a shell, a back shell, and that contains the parachute that we'll see a little bit later. And packed inside of that back shell is the descent stage, which is going to power the rover down to the surface in the last stages of the descent. The rover's tucked up underneath the descent stage, and then to cap it all off on the bottom there's a heat shield, because this thing's going to come slamming into the atmosphere at 5 miles a second. And when it does that, it's going to heat up, and it's going to heat up really, really hot. So,
and how long is the journey? When is it going to go? When is it going to land?
It's going to land August 6th.
5th or 6th, about 8 months?
About 8.5 months from now, yeah. So I have a diagram sort of that whole sequence. We'll look at the diagram, then we'll look at the computer animation of that diagram. Just quickly going through here. So about 10 minutes before the entry into the atmosphere, that cylindrical cruise stage is going to be ejected from the top of the spacecraft. About 8 minutes before, it's going to eject a couple of weights that are on one side of the spacecraft. Now, up to this point, it's been balanced right along the axis of the spacecraft. But when they enter the atmosphere, they want it off balance, because when it enters the atmosphere, they don't want it to go face directly in. They want it to be canted a little bit. They want it to fly like a wing. There are jets on the top of that back shell that they can fire, and if it's not balanced, they can actually fly the spacecraft in an S-curve and actually get closer and closer and refine the landing point by doing that.
They're going to do. Ron, I'm sorry to interrupt.
Oh, sorry.
When you say fly, again, are you saying that the scientists at JPL will be flying this?
There's no one with a joystick at JPL. This is all autonomous. The computers inside the spacecraft know how to do this, because there's a time lag. The speed of light limits us here. It takes this light about 10 minutes to get to Mars, and about 10 minutes to get back, so it's hard to drive. There's a big delay built in. So everything has to be done autonomously. The spacecraft has to know its job. So here we are. It's going to go into the atmosphere. it's going to slow down in hitting the atmosphere. It hits at about 5 miles a second, and it flies itself down. Then it's going to eject a parachute at about 7 miles high, about 900 miles an hour, at about 4 minutes into the entry phase. And that parachute is a supersonic parachute. 900 miles an hour is pretty fast. And that's going to slow it down. First thing they're going to do, though, is they're going to eject the heat shield, because now that we're through the atmosphere, you don't need the heat shield anymore. And then, once the heat shield is off the bottom, there's radar on the descent stage that can detect how high it is. Eventually, they'll drop the descent stage away from the back shell. That'll go off. It'll float off onto somewhere else on Mars. And then the descent stage will fire its rockets and power it down. And then we'll just see the rest happen on the video. So what I'd like to do now is take a look at that happening. So let's switch to that video right now. So here we have, there's the cruise stage just separated on its way down to the surface of Mars. They're going to eject those two little tungsten weights so they can fly it. There they go. And it's going to hit the atmosphere. And that heat shield is going to protect the spacecraft inside from heating up to thousands of degrees. Notice there are those reaction control jets on the spacecraft. That's what is going to allow it to fly itself to a more and more accurate landing. They call it a landing ellipse.
And the landing ellipse is really tiny this time.
It's much smaller than the exploration rovers was, because they actually can do this active flying through the atmosphere. So there's another set of weights they'll eject here coming up pretty quick that'll rebalance the spacecraft. There they go.
And what happens if it's not
So here
balanced?
now the parachute is going to eject. And the parachute's going to slow it down until it's just about a mile up. And then it's going to release the descent stage from the parachute back shell, and it's going to power down. There's 8 engines there. Now the radar is watching the ground.
Those 8 engines slow it down. We're just trying to slow.
They want to slow it down to
a
nothing.
standstill.
Yeah. They want to put that. Now, excuse me. You can't just land this thing with the rover underneath, because how would the rover drive? So the next thing that's going to happen is, well, they're going to watch the ground. There's a camera underneath it. We'll take movies, high-def movies, about 4 frames per second, so they can look for a smooth area to put the rover down on. And then they're going to reel the rover out. 3 wires and an electrical wire there. They put the wheels down. And then they're going to gently, notice only 4 rockets firing now. That rover weighs about a ton. And set it down. As soon as they set it down, they're going to cut all 4 of those wires with explosive bolts. Now freed of its 2,000 pounds, the descent stage flies away, hopefully very far away.
Well, it'll just crash to the surface.
Just crash lands on the surface, leaving the Mars rover all by its lonesome on the surface.
Aww. To do a bunch of self-checks, right?
They're going to do self-checks. They're not going to do anything really for the rest of the day here. The rover is going to sit there and self-check itself out. But on the next morning, go ahead, we'll watch that. On the next morning, as the sun rises over the rover, I don't think the sunrise is actually going to look like that. There's a sundial there on the rover, by the way, the same as on the Mars exploration rovers. It's going to set up the high-gain antenna to the right of the frame there. You can hardly see it happening. And it's going to set up the mast with all the cameras on it. Now, they're not going to move for quite a while, but they are going to do a survey. So the camera is going to turn around. It's going to survey its environment. Here you can see the camera turning around on the mast.
How many cameras are on that mast?
We'll take a close look at that, actually. If you look at those cameras, look at the mast, well, when we get a little closer view here, kind of the view from the camera, you'll notice that the mast has one big eye on the top there. That's a telescope that can do lots of interesting experimentation. It can do telescopic video views. but it also has a laser there to do some chemical analysis. And we'll talk about that in a future webcast. We have so much to talk about today, we really can't talk about the experiments on the rover. But below that telescope, you'll see a square. It's two squares, as a matter of fact. Those are stereo cameras. The one with the big square is the wide-angle camera, and the small square is the telescopic camera. And then next to each of those, there's 4 more little circular cameras. Those are the navigation cameras. The navigation cameras are black and white. The other cameras, the telescopic and wide-angle, those are color video cameras. Those are all going to help. The navigation cameras, again, help navigate the thing, do object avoidance, see what's out in the distance. There are stereo pairs. There's 2 stereo pairs, excuse me, because the rover has 2 computers, A and B, and just in case, of course. And so there's 2 cameras attached to A and 2 cameras attached to B. So let's move on and with this thing. I have a slide of the cameras. I'm going to move along here. There we go. So we're going to look around a little bit more. First day, we're not going to do any driving at all. But we do have to send that data back. So the data that is going to get sent back over a low-gain antenna. It means it doesn't have to use much power because it can relay the information. That cylindrical black can you see in the middle of the frame here, that's the low-gain antenna that's going to send the information back up. Let's go to the next video. Up in orbit around Mars, there are 2 spacecraft, the Mars Reconnaissance Orbiter and Mars Odyssey, that they use as relay stations. And using those, they can send data back to Earth, which is in the background there, at a fairly high rate, at several hundred kilobits per second. Not even as good as you get at home.
I don't know what a kilobit is.
1,000 bits per second. So it's going to take a while for the rover to send back those descent videos. It's going to take a few days before we actually get to see those.
So sometime mid-August.
Yep, sometime mid-August. Let's go. Oh, you're a little ahead of me here. The Mars rover can drive around on the surface of Mars. It has 6 wheels, as you can see. Those 6 wheels are all driven. They all have driving motors on them, so they can be rotated independently of each other. The 4 corner wheels have steering motors, so you can do a lot of very careful and very quick navigation with this thing. The big package on the back of the rover that you're looking at right now is the power source for this rover. You notice this rover does not have any solar cells.
It's a big change from the last rovers, which all you saw was power cells.
Right. This thing on the back is called the MMRTG, which stands for, are you ready for this? Multi-Mission Radioisotope Thermoelectric Generator.
Whew, that's a mouthful.
That's why they say MMRTG.
I see.
And what it has in it is a nuclear source to produce electricity. It's a big lump of plutonium dioxide, basically plutonium. And you get a lot of plutonium together, it gets hot, like a nuclear reactor. It's not a reactor, though. It's just a big lump of plutonium that's hot. And you put something called a thermocouple, which can turn heat into electricity. And so that can generate about little over 100 watts of electricity continuously throughout the entire life of this mission. So you don't have to worry about whether the sun is up or down. You don't have to worry about dust covering the spacecraft. It's always going to have power. Now that MMRTG also charges batteries inside the spacecraft so that they can run during the day at a higher current than 100 watts.
And this mission is 2 Earth years, 1 Martian year.
It's guaranteed for 1 Martian year.
And we think maybe it'll last longer.
Well, if the Mars exploration rovers are any example, they were guaranteed for 90 days, and it's 7 years out now, and one of them is still running. So that's pretty good.
That's pretty good.
So,
here we go.
Okay, we'll go to the next video here. I think you're ahead of me here. Once we start driving, the idea is to look for interesting geology, because the whole point of this mission is to find out whether or not Mars currently could support life, or at some point in the past can support life. And you can tell that by looking at the geology and the mineralogy of Mars. You can tell whether or not the minerals formed in water, whether or not water is present currently. And so We're going to drive around and look at the surface of Mars.
So we're not actually looking for life, but we're
Nope.
looking for signs that life could have existed a couple billion years ago.
Looking for the right kind
Or
of minerals, looking for water, looking for organics. Now, I don't mean by organics, I don't mean life. I mean, well, here the rover is actually spotted. You're a little ahead of me there. Has actually spotted an outcropping, and it has an experiment on there that can actually look at rocks remotely. And our audience, our internet audience, and our live audience here are a little out of sync, but we'll get back in sync. And it's going to be able to drive around and analyze. It can actually analyze the rocks remotely. That big telescope at the top of the mast has in it a laser that can vaporize the rocks, and we'll see that in just a bit here.
That's so cool. And this rover, we imagine, is going to go how many miles? How far will it go? We saw the Pathfinder, when Paul talked about it, just sort of circled around itself.
Yeah.
Where's this one going?
This one can go about, well, they're planning, the guarantee is for 12 miles
12 miles.
from the landing spot.
And do you know how far the MERS went?
The MERS have gone quite a distance, something equivalent to that. The Opportunity is now quite a distance. It's at Endeavour Crater now, which is, it's a lot farther than they had planned ever to go. So let me get to the video that I want to get to here. Here we go. This is the video of doing science.
Okay.
I think this is the right video. Oops. Well, we're seeing different videos here, but here you can see our live audience, our internet audience can see the rover looking at the rocks. We're almost in sync here, and it can send out a laser and vaporize a portion of rock. When it does that, the little spark that's created at the rock, they can look at that light, and they can analyze the light from that spark, and they can tell what the rocks are made of. That's a really cool experiment. It's called the ChemCam, chemistry camera. Yep. It also has on it an arm that can extend and be a little more intimate than the ChemCam can with the minerals and rocks out there. That instrument the arm has 3 experiments on it. It has a drill that they can collect material from the environment. It has an X-ray spectrophotometer, and it has a hand lens. Everybody knows that any geologist worth their salt takes their hand lens out and looks at the rock. So here what you're seeing is the drilling into the rock. It can then pick up that dust and deliver it back to the experiments inside the rover. It's tilting its head to sift through the soil there, because they only want to have a certain amount, and they only want to have a certain grain size that they drop into the rover. So now what it's going to do is drop that soil into the rover. And it falls into some experiments inside. There's a chemistry lab. There's 2 experiments inside the rover body itself that are going to look at the mineralogy and what crystals and what elements there are inside these samples.
And so they're looking for, I guess, carbon being the basic building block of life. They're looking
for anything.
There?
This will show any kind of element. This is doing X-ray diffraction. They can also do X-ray fluorescence spectroscopy. And then there's another experiment, which we're not going to show you here, that can actually analyze chemical elements in the water, in the soil by heating it up and looking at the gas that's given off. It does a mass spectrometer and a gas chromatograph.
So we're just looking to learn what the chemical makeup is of the rock.
That's right.
And hopefully that information
that tells you the history.
The history, whether or not it's been habitable in the past, or perhaps if it's possible that there's life there today.
Yes. So I have a slide here of what the actual rover looks like, if you'd like to take a look at that. This is the actual rover, and it's quite large. It's about the size of a, well, I don't want to say a minivan, maybe a small SUV, maybe a RAV or something like that. And you can see there that it has the 6 wheels, and the arm there is in the front. It has actually 8 more cameras that aren't on the mast. There are some cameras that are mounted down low on the chassis to look at where the wheels actually are. So they can. This is called the hazard avoidance cameras. And again, there's 8 of them because there's 2 stereo pairs front and 2 stereo pairs back. So it's a pretty advanced piece of machinery. So here's a kind of a diagram of the location of all that stuff. And I don't know whether we want to go into all of that or not, but the mast has the mast cams and the chem cam. And we didn't see this, but on the mast itself, there's also 2 little stubs that stick out, and those are the environmental monitors. It's actually a weather station. They can measure on Mars. They can measure the wind speed and direction, the temperature, the barometric pressure, the relative humidity, and there's also a sensor for how much ultraviolet light is on the spacecraft. Other interesting experiments are there's a one here called the RAD. They want to measure how much radiation is hitting the spacecraft too, and that's for future manned missions. They want to know how much radiation is you'll be exposed to on the surface of Mars. So there we go, Curiosity on the surface of Mars.
All right. Well, great. So does that wrap it up?
Well, except for a picture of how big it is, maybe.
Well, let's talk about that, because I think the one question we get more than anything else is exactly how big is that rover? And the answer is it's really, really big. So this is a great diagram we got from our friends at NASA that compares a person with the rover. We're hoping to have a model of the rover here in August.
Full scale.
So if you check back here in just a few months at the Exploratorium, hopefully we'll be able to have a big full-size model that y'all can check out. Does that wrap it up, Ron?
That wraps it up.
All right.
I think we've already run over.
We certainly have run over time. Thank you so much for joining us. We'd also like to thank the Jim Clark Endowment for Internet Education and the McBean Family Foundation for making the webcast available today.